All right, we're going to finish up. We're going to finish up a few things on chapter 18 and then review for the test. All right, so we talked a little bit about this table. Very, very, very important table. If you understand this table, you should be able to do all of the chapter 18 problems. All right, so when you have a negative delta H, so delta H, negative, that means it is exothermic. All right, so we've already done this in chapter 6, delta H positive, you're endothermic. You have to know heat is released, heat is a product. If you are exothermic, heat is a reactant that is absorbed when it is a endothermic reaction. All right, and so your delta S. So delta S positive. Delta S is entropy. Entropy is disorder. Positive delta S means more disorder. So you're going to have more gases on the product side than you have on the reactant side. All right. Of course, if it's negative, then it is, well, you can call it a couple of things. But since it's negative, I'm going to use a negative answer. And so that is less disorder. Of course, you can call it more order. I'm going to say when it's negative, it is less disorder because delta S is disorder. All right. So then you have your delta G. So when your delta G is negative, that means it's spontaneous. When your delta G is positive, that means you are not spontaneous. And spontaneous is in the forward reaction, spontaneous. All right, when delta G is positive, then you are non-spontaneous. All right, so now a negative, and so the equation that we need to know is the delta G is equal to delta H minus T delta S, and I'll say it again and again and again, that your delta H, you get off the table, products minus reactants, delta H, it doesn't matter what the temperature is, that is your delta H. Same with delta S, you get your S values off the table, you have your products minus reactants, you have your delta S, doesn't matter what the temperature is. Delta G, if you're using the table, products minus reactants, that is only true at 25 degrees Celsius. At any other temperature, you have to get the delta H and the delta S and calculate the delta G by taking your delta H minus your T delta S. All right, so if our delta H is negative, so I'll put a little negative here where my delta H is, and my delta S is positive, and I'll put a little positive here, indicating that my delta S is positive. Temperature is, in Kelvin, always a positive number, and so you have a negative number minus a positive number, which means you're going to have a more negative answer. So no matter what you do with your temperature, it will always give you a negative delta G. So when you have a negative delta H and a positive delta S, there is no way to make this non-spontaneous. It is spontaneous no matter what temperature you put in. Any temperature you put in here, you will get a negative delta G value. All right, and the example is here. The only thing that we can predict about this example is that you have a solid going to two liquids and, very importantly, two gases. So we know for sure that the delta S is positive, and that's what it says right there as well. All right, but here's an example where it's exothermic and the delta S is positive. This reaction of fermentation is spontaneous at all temperatures. If we do the reverse, if I take an endothermic reaction where the delta H then is positive, and we're going to have something that is going to less disorder, a negative delta S. So if this is positive and this is now negative, and temperature is always positive. So now you've got a positive number minus the product of a positive and negative, which is going to be negative. And when you subtract a negative, that is a positive. And so there's no way for the delta G to become negative. It would be positive at all temperatures. And so this is non-spontaneous at all temperatures. So, or you could write never spontaneous. All right, and so the only thing you can predict here is you can see that you have 3 moles of gas on the left going to 2 moles of gas on the right. We have less disorder. Delta S is negative, but that one is also endothermic. You can always, well, you can usually predict the delta S. Sometimes you predict it to be essentially 0, but it's not going to be 0. You have to calculate it. So you can't predict every delta S, but when there's a difference in gases, you can always predict the sign of delta S. Some reactions you can predict your delta H, but most you cannot, and so you have to do products minus reactants. All right, now if they are the same sign, so if we have an exothermic reaction, negative delta G, and a reaction that is going to less disorder, negative delta S, now we can be spontaneous or we can be non-spontaneous. All right, and so I always stick with when are we spontaneous? So when it's negative and negative. All right, so you have your delta G is equal to delta H minus T delta S. So the delta H is negative, the delta S is negative. All right, again, temperature is always positive. So you have a negative number minus the product of a positive and negative number, so minus a negative number, and so you have a minus plus a number. In order for this plus this number to not override this minus, if we had a low temperature, then this product of temperature times your delta S would be a very small number, and so you have a negative, and then you'll be adding a very small number, and it would still be negative. So we say this is spontaneous when we have a low temperature. All right, and so what's easy to remember is negative, negative, spontaneous, low temperature. All right, and we will see that that is a not very helpful term, low temperature. We're going to actually calculate that temperature. All right, and so then, of course, if it's the opposite of that, I have an endothermic reaction going to more disorder. And if we look at the reactions over here, this one had 4 gases going to no gases, and so your delta S here is going to less disorder. And here we have a solid, 2 solids going to an aqueous and 2 gases. So we're definitely going to more disorder. All right, so you can all 4 of these can easily predict the sign of delta S. The delta H had to be given. All right, and so now when it's both positive and you have your delta G is equal to delta H, that is now positive, minus temperature, always positive, it's in Kelvin, and delta S now positive. So now we have a positive number minus a number. In order for this number to override the positive delta H, now we need a large negative value. So that means the higher the temperature, the larger this negative value would be. And so this is going to be spontaneous at high temperatures. So negative, negative, spontaneous, low. Positive, positive, spontaneous, high. All right, so now we're at equilibrium when delta G is 0. So we're at the perfect equilibrium. And if it's plus or minus 10, we still say we're at equilibrium. But we're at the perfect equilibrium when your delta G is 0. All right, and so we plug in 0 for delta G. And that is equal to delta H minus T delta S. Add T delta S to both sides. T delta S is equal to delta H. Divide both sides by delta S. And your temperature is your delta H divided by your delta S. And so when it says you're spontaneous at low or high temperature, the temperature that we're talking about is when you take your delta H and you divide by your delta S. That is the temperature that we are calling a low or high temperature. So if they were both negative, then it would have to be less than this temperature that you calculate, if they are both to be spontaneous. If they're both positive, then the temperature would have to be higher than this temperature that you calculate. And so remember that temperature is Kelvin, always positive. The only way that you're going to get a positive number out of this division is when they are both negative, delta H and delta S both negative. Negative divided by negative gives you a positive. Or both positives. Of course, a positive number divided by a positive number is a positive number. You cannot get an answer if you have a negative and a positive, because that would give you a negative temperature. All right, so that's why that if you are negative delta H and you're positive delta S, you're spontaneous at every temperature. And if you're positive delta H and negative delta S, then you're never spontaneous. You are non-spontaneous at any temperature. So the only time you can calculate a temperature is when they are both negative or they are both positive, the delta H and the delta S. All right, so let's do a calculation. All right, what is the delta G naught at 1,000 degrees Celsius? As soon as I see that, I add 273. All right, for the following reaction. So here is the reaction. You got a solid going to a solid and a gas. So you can know one thing for sure, and that one thing is your delta S is positive. We are going to more disorder, no gases going to a gas. All right, and so the question is the reaction spontaneous at 1,000 degrees Celsius? So what we got to do is we find our delta G. If it's negative, it's spontaneous. If it's positive, it's not spontaneous. All right, and then the second part is, what is the value of Kp? Well, we're going to use the equation that the delta G is equal to negative RT ln KEQ. And so when we do our KEQ for this reaction, solids we don't put in, so we're not putting in either one of our solids. They do not go into our equilibrium expressions. If you have a gas, it is in terms of pressure. So this is simply the pressure of CO2. When you have an equilibrium constant that only contains pressures, then that is a Kp. If you had an equilibrium expression that only contained concentrations, then you have a Kc. And so here they're saying calculate Kp. In this case, the Keq is exactly the same thing as the Kp. All right, so we're going to find delta G. We're going to put it into our equation, and we will then find our Keq. And then it says, what is the pressure of CO2? Well, the pressure of CO2 is equal to Kp. All right, so we're at 1,000 degrees Celsius, so we cannot use delta G off the table. So we can find delta H. We're going to find that by taking delta H products minus delta H reactants. We can find delta S. That's taking the S of the products minus the S of reactants. Delta G, we cannot do delta G products minus delta G reactants. This is only at 25. So you cannot use that equation to find the delta G. And so to find delta G, you're going to take your delta H and then subtract your T delta S. That is the only way to find delta G when you are not at 25 degrees Celsius. And you can find it that way if you're at 25 degrees Celsius as well. But at 25, normally you'll just do the products minus reactants. But you can only do that at 25. So here's the values for our delta H. There's the values for our delta S. And so we will simply take our products. We're going to add our negative 635.1 kilojoules per mole. There's 1 mole of that. We're going to take our negative 393.5 kilojoules per mole. There's 1 mole of that. Add those up. That's our products. Then we're going to subtract a negative number, which is then going to be a positive 1206.9. And we do our products minus reactants. Same thing here. Products, add these two numbers, minus reactants, that number, and you have your delta H and you have your delta S. All right, so once you have your delta H, which is your 178.3 kilojoules, and you have your delta S, which is 159.0 joules per Kelvin. Always be aware of your units. Delta H, always in kilojoules on the tables. Delta S, always joules per Kelvin on the table. Delta G is always in kilojoules on the tables. All right, so now we're going to plug it into our equation, delta H minus T delta S, because that's the only way we can find delta G at this temperature. Any temperature that's not 25, you have to use this equation. Units have to work out. So since delta G is normally given in kilojoules, I'm going to leave my delta H in kilojoules, and I'm going to convert my delta S into kilojoules. All right, so my temperature in Kelvin is 1,273, and now my delta S converted to kilojoules per Kelvin is 0.159 kilojoules per Kelvin. All right, so then I add those up. I take my 178.3 minus the 1273 times the 0.159, and I get a negative 24.1 kilojoules for my delta G. And so this reaction is spontaneous. Anytime you get a negative delta G, it's spontaneous. But remember, if that delta G is between the plus and minus 10, it is called an equilibrium, because spontaneous means you have a lot more products than reactants. Non-spontaneous means you're not going to the right, you have a lot more reactants. Equilibrium means you have similar amounts of your products and reactants. So a spontaneous reaction, lots of products. When you find your K value, your K is going to be a large number. And what does large number mean? It just means a number that's greater than 1. So your KEQ is going to be large. Again, large just means greater than 1. And small would mean less than 1. All right. So now we can find our KEQ. So we have our equation. Delta G is equal to negative RT ln KEQ, which in this reaction is the same as our KP. All right, I like to leave my R in joules. So I will, for this reaction, always convert my delta G into joules. So negative 24.1 kilojoules. All right, so instead of putting the K, I put times 10 to the third because I know that K is 1,000 or 10 to the third joules. And so now I can put in my 8.314 joules per mole Kelvin, and that is joules per mole. All right, and now my temperature, which must be in Kelvin, 1273, and then ln KEQ. All right, and so then you divide negative 8.314 and 1,273 on both sides. And you get 157. That is not what you get. Push the wrong button. You get 2.277. And that's equal to ln KEQ, and then you push your second ln, your e to the x button, and you get 9.7. All right, so it said it was going to be a large number. That is not what I would consider a large number. But large number, again, just means a number that is greater than 1. 9.7 is greater than 1, so it's considered a large number. And that is equal to the Kp. That is equal to the pressure of CO2. Now, that is fine for calling that Kp. That's also fine for calling that Keq. That is not fine for calling it pressure of CO2, because the pressure of CO2 is 9.7, and now pressure must have a unit. The K values are not required to have a unit, but your pressures must have a unit. And 3 sig figs everywhere. I'm going to go with 9.75. 9.75. All right. So now I want to know, at what temperature is this reaction spontaneous? So at what temperature is this reaction spontaneous? All right, so we need to find our delta H and our delta S. All right, we already have those numbers. The delta H, all right, delta H is 178.3. So that is 178.3 kilojoules per mole. All right, and then our delta S is right there at, I'm going to put it in the correct units, 0.1590 kilojoules per mole Kelvin. So your kilojoules must cancel your kilojoules. And so when you take 178.3 and divide by 1.1590, you get 1,121. All right, and so since my delta H is a positive number and my delta S is a positive number, I know that this is spontaneous at high temperatures. All right. So, but what does that mean? That means that higher than this temperature. So it is spontaneous when your temperature is greater than 1,121 Kelvin. All right, so you could have said, oh, look, I have a 1,273 Kelvin. They're both positive. It's spontaneous at high temperature, so it's spontaneous. Well, if you would have guessed that, you would have guessed right. However, if the question would have been slightly changed to, instead of 1,000 degrees Celsius, what if the problem said 1,000 Kelvin? Again, a very high temperature. All right, and so I know what the answer is going to be. That temperature is less than 1,121. This is not going to be spontaneous. Is that a high temperature? Well, yes, but it is not high enough to make it spontaneous. High temperature means the temperature higher than your delta H divided by your delta S. So it's only spontaneous when the temperature is higher than 1,121 for this reaction. For other reactions, it would be different. You have to take your delta H, divide by your delta S to get that temperature. So let's go ahead and calculate our delta G at 1,000 Kelvin. It's pretty simple. Your delta H doesn't change. Your delta S doesn't change. All you got to do is, instead of putting in your 1273, is to put in the 1,000. And when you do that, you get a positive number. It comes out 178.3 minus 159.0 when you multiply that number. And so here, if it's at 1,000, your delta G is a positive 19.3 kilojoules, non-spontaneous. All right, and so that one we knew would be a positive number because that temperature was less than 1,121, not greater than the 1,121. All right. So then, of course, we know that our when you stick in 298, which is 25 degrees Celsius, it's even going to be more non-spontaneous. It's going to be more positive, your delta G. So if you were to find the delta G at 25, you can look up the numbers off the chart, or you put in your 298 here. Put in 298, and now you've got your delta G at 25 degrees Celsius. Again, your delta H and your delta S are going to be the same regardless of your temperature. All right, so let's do a couple of the homework problems. All right, we're going to start with the problem 18.66. And the reaction is 2HGO solid goes to 2HG gas and O2 gas. All right, so we see that we have no gases, a solid, going to three gases, so we know that we're going to more disorder. So we know for sure that when we calculate our delta S, it will be positive. All right, so estimate temperature at which this is spontaneous. All right, so I'm going to say calculate delta H, delta S, delta G, and KEQ at 25 degrees Celsius. And then at what temperatures, if any, will this reaction be spontaneous? All right, so we go to our table. And so they told us a table number to go to. Appendix C has the tables, yes, so we get our data. All right, so we have our data for delta H. All right, so I look at my delta H, wrote S, but I said H, delta H. All right, so for my mercury oxide, mercury 2 oxide, I got negative 90.79 kilojoules per mole. For my mercury gas, 61.38 kilojoules per mole. And then, of course, my delta H for elements in their natural state are 0. Note that mercury in its natural state is a liquid, not a gas. That is why it has a value. When we look up our S values for HGO, it is 70.27. And now that is in joules per mole Kelvin. All right, and then for mercury gas, it is 174.9 joules per mole Kelvin. And then for the oxygen, it was 205.0 joules per mole Kelvin. And we need delta G at 25, so let's go ahead and get the delta G. You can find it by using your delta H and your delta S in the equation. Since we're at 25, we can just do products minus reactants. So I looked up the delta G values, negative 58.49 kilojoules per mole, 31.91 kilojoules per mole. And just like your delta H, delta G for elements in their natural state will be 0. All right, so let's calculate the delta H. So you take your delta H products minus delta H reactants. Now we have coefficients. All right, so your products, you have 2 moles of Hg gas, mercury gas, and so it is 2 times 61.38 plus 1 times 0. You don't have to write 1 times 0, but the oxygen is 0. There's 1 mole of that. So that's your products minus the reactants. Again, you have a coefficient of 2 moles. And for each one, you have a negative 90.79. All right, and so you have a minus a negative, so that is going to add. All right, so you plug that into your equation. You've got your 61.38 times 2. All right, so it's 122.76 minus a negative plus 90.79 times 2. And that gives you 304.34. So your delta H is 304.34 kilojoules. All right, and so this is endothermic. All right, so anytime you have a positive delta H, you have an endothermic reaction. All right, we're going to do the same thing, this time with the delta S. S of products minus S of reactants. All right, and so again, you're going to have 2 times your 174.9 joules per mole Kelvin. So your 2 moles, so the moles cancel. All right, this time it's not 0, plus 1, you don't have to write the 1, times the 205.0. So there are your products minus your reactants. All right, for that you have 2 moles of your mercury 2 oxide reactant times the 70.27. All right, so your products 174.9 times 2 plus 205. All right, so that's 554.8 minus 2 times 70.27. And that gives you 414.26. And that is in joules per Kelvin. All right, and I'm not sure that we predicted that. We should have predicted that first. Oh, we did. All right, so we had a solid going to 2 gases, so we predicted a positive delta S, and that is what we got. All right, so we're going to more gases, more disorder. All right, now the delta G. So we're at 25 degrees Celsius, so we can use the numbers off of the chart. And so we are at 25 degrees Celsius, so making a note of that. So we can do delta G products minus delta G reactants. And so your products, you have your 2 times your 31.91. And then 0, so your products minus reactants 2 times the negative 58.49. So you got your 31.91 times 2 minus a negative plus 2 times 58.49. And so your delta G is a positive 180.8. kilojoules. And so this is non-spontaneous. All right, so that means that a reaction doesn't go to the right, which means you don't have very many products. You have mostly reactants. So products over reactants, your K value is going to be very small. All right, small again just means less than 1. So you're going to find a number that is going to be point something, less than 1. And so we can solve for that. Delta G is equal to negative RT ln KEQ. All right, so here I'm going to work in joules. 180.8 times 10 to the third joules per mole is equal to negative 8.314 joules per mole Kelvin. And the temperature, which is 298, we're at 25 degrees Celsius, and we can calculate our KEQ. All right, and so we then divide both sides by negative 8.314 and divide by the 298. And we get a negative 72.97 for LNKEQ. All right, and so then you take your second ln, your e to the x button, and you get 2.030 times 10 to the minus 32. All right, so that's a very small KEQ. That is 0.31 zeros and then a 2030. All right, so we predicted a small number, a number less than 1. We got a very small number. All right, so now the question is, at what temperature is this reaction spontaneous? We see that we have a delta H value that is positive 304.34. Kilojoules per mole. That is my delta H, positive. And then my delta S, we calculated 414.26 joules per mole Kelvin. All right, and so when you have a positive delta S, H, and a positive delta S, we know that this is going to be spontaneous at high temperatures. All right, so that would be a very generic question. I need to know, what are these high temperatures? Is 1,000 degrees high enough? Is 100 degrees high enough? What temperature do I have to be at? So your temperature that you have to be at is found by taking your delta H and dividing by your delta S, and making sure that joules cancel joules or kilojoules cancel kilojoules. I'll work in kilojoules. So 304.34 kilojoules per mole. And then I have my delta S, which is 0.41426 kilojoules per mole Kelvin, because the kilojoules have to cancel the kilojoules. 1 over Kelvin gives you Kelvin. So 304.34 divided by 0.41426 gives you a temperature of 734.7. No, 734.66. All right, so that's a lot of sig figs for a temperature. And so I will say that your temperature has to be greater than 735 Kelvin to be spontaneous. All right, and so, and I'm in Kelvin. All right, so if we want to do a calculation, so let's say calculate delta G and KEQ at 1,000 Kelvin. All right, so again, delta G you cannot get by products minus reactants. That's only at 25. The only way to get the delta G is by the delta H minus T delta S equation. All right, and so we just plug in our numbers. So our delta G at this temperature is the delta H, which is the same at any temperature, 304.34 kilojoules per mole, minus the temperature. We're at Kelvin, 1000 Kelvin. And we know that that is greater than 735. We better get a negative number for this. And our delta S, which has to be in kilojoules, is a 0.41426 kilojoules per mole Kelvin. And so your kelvins cancel, and now you have kilojoules minus kilojoules, and you have kilojoules for your delta G. You got your 304.34 minus 1,000 times 4.41426. And that gives you a negative 109.92. All right, and so that is spontaneous. And when you're spontaneous, that means you have lots of products, very few reactants. You're going to have a large K value. All right, so when we calculate it, all right, we have negative 109.92 times 10 to the third joules is equal to negative 8.314 joules per mole Kelvin. Joules per mole. All right, and then your temperature, 1000 Kelvin, ln KEQ. Right, so we have, okay, so then divide both sides by negative 8.314 and divide both sides by 1,000. You get a 13.22 is equal to ln KEQ. 13.22 is equal to ln KEQ. And then you take your e to the x button and you get 1.664 times 10 to the 13. Is that right? Sure. That is not pushed correctly. Okay. Not sure what I did different. That is not what you get for that answer. So e to the 13.22 is 5.519 times 10 to the 1, 2, 5. I think I did. I pushed the LOG button instead of the LN button. All right, so that is my KEQ. All right, so again, spontaneous, large K. What does that mean? Greater than 1. Yes, this one is 10 to the 5th, much, much greater than 1. All right. Try number 64. 18.64. All right, so use the table to do this one. This one is nitrogen gas plus oxygen gas yields 2 NO gas. Now here's one where you have two gases going to two gases. And so you would say that your delta S is essentially 0. You cannot predict the sign of delta H. Of delta S. All right, so it's going to be small because you have two gases going to two gases. You cannot tell me whether it's going to be positive or negative. You have to calculate it. All right, so you can't predict it. You must calculate it. And this is not one where you would know the delta H either. All right, so there's your reaction. What is the question? Calculate Kp at 2000 degrees Celsius. All right, so I will immediately erase that, 2273 Kelvin. I automatically add my 273 to make it Kelvin, because if you use Celsius, you will always get the wrong answer. All right, so we need to find our, in order to calculate Kp at this temperature, I have to calculate delta G at 2273 Kelvin. All right, which means I need to find that by taking the delta G is equal to your delta H minus T delta S. All right, I cannot do products minus reactants. That's only at 25 degrees Celsius. So I have to find my delta H, my delta S, calculate the delta G, and then to calculate Kp, I have my delta G is equal to negative RT ln KEQ. All right, now is KEQ the same as Kp? Well, let's do our expression. So the expression for KEQ for this reaction, gases have to go in pressures. So that's the pressure of NO raised to its coefficient of 2, pressure of N2, and pressure of O2. So whenever you're given a KEQ and everything in that KEQ is in pressures, now you have a Kp. And so that's why the problem asks for you to calculate the Kp. That is the same as the KEQ. All right, so let's look up our numbers. We need our delta H values and our S values off of the table. All right, so here are the S values for N2, 153.2. And the S value is 205.0. The S value is 210.6. The delta H values, elements in their natural state, 0, NO, 90.29. All right, so now we simply take the products minus reactants to get both the delta H and the delta S. All right, so your delta H, you take your products, 2 times 90.29 kilojoules per mole, minus reactants, 0 plus 0, they're both 0, so that's it. So your delta H here is 180.58 kilojoules. All right, so it is positive, it is endothermic. All right, and so now we have to calculate our delta S. We could not predict. We had 2 moles going to 2 moles of gas. All right, so now we're going to calculate it. 2 times the 210.6 joules per mole Kelvin. All right, so that's your products. Minus reactants, 153.2 joules per mole Kelvin, and 205.0 joules per mole Kelvin. And both of those have 1 mole. All right, so when we push the buttons on our calculator, 210.6 times 2 minus 153.2, 205. All right, we get 63. The delta S is positive. We could not predict that from the given reaction, but we calculated. It is a positive 63.0 joules per Kelvin. All right, and so this one is going to more disorder. All right, so now we're going to find the delta G at 2000 degrees Celsius. All right, so the delta G at 2000 degrees Celsius, which was changed to 2273 Kelvin. All right, so your delta G is equal to your delta H, which we calculated as 180.58 kilojoules, minus T, the temperature we're at is 2273 Kelvin, and the delta S, which has to be in kilojoules, so that is a 0.0630 kilojoules per Kelvin. The Kelvins cancel, and now you have your delta G. So 180.58 minus 2,273 times 0.0630, and we get 37.4. All right, and so this is non-spontaneous. All right, and so when will this be spontaneous? So at what temperatures, if any, is this spontaneous? All right, so your delta H is positive, your delta S is positive, so there will be a temperature. So your delta H, 180.58 kilojoules, divided by your delta S, 0.0630 kilojoules per Kelvin. So you take your 180.58 and divide by the 0.063, and you get 2,866. 2,870 if you want 3 sig figs. All right, so our temperature, and so the temperature that we get is 2,870. Since they are both higher, this is not the answer. At what temperature is this spontaneous? Actually, at 2,870, you are delta G of 0, not negative. And so your temperature has to be greater than 2,870 Kelvin. All right, and so we see that this temperature was very hot, but it was only 2,273. It is still a non-spontaneous reaction. The temperature would have to get up to 2,870 for that to be spontaneous. All right, we need to find our K value. And so this is non-spontaneous, so we know that there's not going to be very many products. We're going to have a low KEQ value, a small KEQ value, a number less than 1 for the KEQ. All right, and so our delta G is equal to negative RT ln KEQ. So our delta G is 37.4 kilojoules times 10 to the third joules. Kilojoules is times 10 to the third joules. That's equal to negative 8.314 joules per mole Kelvin. And the temperature that we were at in this problem was 2,273 Kelvin. And now we're going to find our KEQ. So 37.4 to the third divided by negative 8.314. Also divide both sides by 2,273. And you get negative 1.979. It's equal to the ln of KEQ, and now you push your e to the x button, and you get a KEQ that is small. It is 0.00630 0.1382. Well, 0.138. All right, so your KEQ is 0.138. So that is a small number. What number are we basing that on? The number 1. So it is less than 1. Anytime you are non-spontaneous, your K value will be less than 1. All right, if we go to 18.56, we're just writing an expression for the KEQ. So CO gas plus 2H2 gas yields CH3OH gas. All right, so we have 3 moles of gas going to 1 mole of gas. So what we can do is predict the sign of delta S. So delta S, we are going to less disorder. 3 moles of gas going to 1 mole of gas. So we know our delta S is going to be negative, but that's not our question. It is to do the KEQ. If you have gases, they have to be in pressures. All of these are gases. They all have to be in pressures. All right, and so when you have an expression where everything is in pressure, that is also Kp. For part B, it is 2Ag plus and CrO4 minus 2 going to Ag2CrO4 solid. All right, so your products, solids, are not included in our equilibrium expression. So just 1 over the reactants, Ag plus squared, and CrO4 minus 2. All right, since these are both aqueous, then we put them in concentrations in molarity. And so this, since they're both in molarities, that is the same as your Kc. So remember that this is moles per liter, or molarity, and pressure is in atmospheres. Now, if we have one that's in part C, where we have calcium carbonate, which is a solid, and to that we add acid, so 2H plus, and that's in equilibrium with calcium plus 2 and H2O liquid and CO2 gas. Oh, we didn't do the delta. For this reaction here, since there are no gases, if there are no gases, you cannot predict your delta S. So you must get the numbers off the table, calculate your delta S. It may be positive, it may be negative. You cannot predict the sign unless you have a difference in gases on both sides, or it's just a phase of the same molecule. All right, so here we have no gases going to 1 gas, so we know that this delta S is positive. We're going to more disorder. All right, but that's not the question. The question is calculate the expression, not calculate, give the expression for KEQ. All right, so we have our products, calcium plus 2, concentration. Liquid, water, not put in. Gas must be in pressure. Pressure, CO2, over solids, not put in the expression for equilibrium. H plus squared. So this KEQ is only equal to KEQ. It is not KP because everything's not in pressure. It's not KC because everything's not in concentration. And so this is simply a KEQ, where gases and aqueous are in the same reaction. A lot of these problems are finding the values off the chart, doing products minus reactants. Make sure that you can do that and get those right every time. Do not forget to multiply by the coefficients. Let's try 54. That one's a little different. (18.54) maximum work. So work max is equal to delta G. All right, and so we are looking for the delta G. We're at 25 degrees Celsius. Since we're at 25 degrees Celsius, we can get the delta G of the given reaction by doing products minus reactants. We don't have to get delta H and delta S. All right, so the first thing we want to do is find the delta G, but then we want that for 3.65 grams of zinc from the reaction of zinc solid plus 2H plus yields zinc plus 2 plus H2 gas. All right, and so we find our table of delta G's. We're at 25 degrees Celsius, so we can do it that way. All right, elements in their natural state, 0. H plus, not an element in its natural state, but H plus is 0 off the table. Your zinc plus 2 is a negative 147.0 kilojoules per mole. And H2 gas is hydrogen in its natural state and is 0. And so the delta G for this reaction is your products, negative 147.0 kilojoules per mole, plus 0, minus reactants, 0 and 0. So that's it. So this reaction is spontaneous. All right, and it is a negative 147.0 kilojoules per mole. So just like we would do the delta H, we do the delta G. All right, and so it is then your delta G negative 147.0 kilojoules for that balanced reaction. So that balanced reactant, that is for 1 mole of zinc. If they would have given us information on acid, it is for 2 moles of the acid. All right, and so we know that we have negative 147.0 kilojoules for every 1 mole of zinc. All right, but we have 3.65 grams of zinc. All right, so what we can do is we can go from kilojoules per mole to kilojoules per gram. In order to do that, we need the molar mass of zinc. All right, so you got to find a periodic table and get your molar mass of zinc. I think it's, I don't know what the molar mass of zinc is. Oh yeah, 65.41, good. 65.41 grams per mole of zinc. And so the moles of zinc cancel. And so you can actually get another answer that is your negative 147 divided by your 65.41, which would tell you that you would get, you can do 2.247 kilojoules of work for every gram of zinc. And of course, we have 3.65 grams of zinc. You could do this all in one row as well, but if you wanted, this is the kilojoules per mole of zinc, this is the kilojoules per gram of zinc, and we have 3.65 grams of zinc. And so we can do 8.20 kilojoules of work. So that would be a negative 8.20 kilojoules. So we can do 8.20 kilojoules of work for 3.65 grams of zinc running that reaction. All right, so kilojoules in delta G is in kilojoules per mole. And so you look at the balanced reaction just like you would for the delta H. All right, you have to use the coefficients. Zinc happened to be 1 here, so it's just per 1 mole of zinc. But if it was the acid again, it would be, you would get negative 147.0 kilojoules for 2 moles of H plus. Let's do one of my favorites. All right, let's do this one. H2O solid going to H2O liquid, 25 degrees Celsius. Determine sign of delta H, delta S, delta G. At what temperature, if any, is this spontaneous? All right, so this is one that you know. This is H2O, H2O solid. We call it ice. All right, so this is ice. And it is, of course, changing to H2O liquid, which we call water. And we are at 25 degrees Celsius. All right, and so the sign of delta H. So, of course, you stick an ice cube in your hand and it's going to melt and your hand gets cold. If your hand is getting cold, that indicates an endothermic reaction because we know that we have to heat ice to make it turn into a liquid. All right, so you heat the ice, it turns into a liquid. So the sign of delta H is positive. Delta S, there are no gases, but we have H2O solid, and we know that solids are going to have more order than a liquid. Solids, molecules don't move around. They vibrate, but they don't move around. Water, the molecules are moving around. And so we know that we are going to more disorder. Any solid going to a liquid, the same molecule, this is just melting, you're going to have more disorder as a liquid than a solid. And so we know that our delta S is positive. Now the delta G. So when we take an ice cube and we put it in a room at 25 degrees Celsius, it will automatically melt. There is nothing else that we have to do to it. We just set it at room temperature and that ice cube will melt. That is a spontaneous process at that temperature. All right, and so here it is at what temperature, if any, is this spontaneous? All right, now you know this reaction, you know this phase change, you know that water will freeze and ice will melt at 0 degrees Celsius. That is the freezing point, all right, or 273 Kelvin. So what do you know? You know the temperature. If your temperature, note that you have a positive delta H and a positive delta S. And we also know that when we take our delta H and divide by our delta S, we are going to get 273 because we already know that temperature because we know this process of melting an ice cube. All right, and so now we know that our temperature is going to be spontaneous when the temperature is greater than, both of them being plus, greater than 273 Kelvin. Or, of course, you could say the temperature greater than 0 degrees Celsius. So ice is going to spontaneously turn into liquid water when the temperature is greater than 0. All right, we could take another, basically the exact same thing, and I can take H2O gas and go to H2O liquid. All right, so in this case, you see you have to always heat the liquid to make it a gas, delta H, negative. We are at 25 degrees Celsius. So delta S, we have a gas all over the place going to a liquid. We're going to less this order. And so now we see we have both negatives. And so we know that when the temperature is less than, and we know this point, 100 degrees Celsius or 373 Kelvin, we know that when the temperature is less than 373 Kelvin, then delta G would be negative. At 25, we will condense it. So here, your delta G, when you have your 298, which is where we're at, that is less than 373. So your delta G, this is spontaneous, that at room temperature, you will condense your steam. All right, no class tomorrow. We will meet on Wednesday and keep reviewing for the test on Thursday.